So on your homework, and this is one reason why I talk about your homework on the board before I give them to you. Feel free to correct me on this. You all have Bradley to thank for this, because I swear that I thought that I had already given you this result, which I hadn't. And it's the one I emailed to you all, whenever I did it last week. And so, I meant to, I really thought I had done this result earlier, but I hadn't. But I want to go through it because there's nothing that we need as far as, machinery to do this. So I'll remember this correctly, like it's in my notes. And this, well, I'm not going to say you need this result, but I needed it for the proof I gave for 2C on the homework, right? So if you end up going down the path I did, you might need this. Of course, there's always more than only skin cap. Let R be infinitely closed. And quasilocal. So it's an integrally closed domain, and it's got a unique maximal ideal. And let U be an element of the quotient field. If U is a polynomial equation over R, if the U is root, of polynomial equation, actually, root, let's say, of a polynomial in R, let's say. Okay. If U happens to be the root of some polynomial, coefficients in R, and at least one coefficient of fx is a unit, then U or U inverse is in R. Okay, so this sort of generalizes the notion of integrality. So here's the deal. Now, your range is pretty specialized. It's got to be integrally closed. It's got to be quasi-local. Suppose you have a polynomial, and this term generalizes a monic polynomial. So it doesn't have to be monic, but at least one of the terms, could be the constant term or any intermediate term, has a coefficient that's unit, then either U or its inverse is in there. And notice, of course, if the leading term is by the way, notice that if the leading term is a unit, then U is in R, right? And if the constant term is a unit, then U inverse is in R. And of course, in both cases, it may be both of them, but at least that. But the interesting part is it can be any of the terms. Okay, so let's write down the equation, and I'm only going to pay attention to the first two terms, because this is basically an inductive or reduction argument. So suppose U is a root of A xn b xn minus 1. I'm all focused on that. So A U n is B U n minus 1 is equal to 0. Okay. If A is a unit in R, then done. Because U is in R as R Is n equals. Right. Let me also point out, note A times U is in R. Does anybody see why that's?
Well, we multiply the whole thing by a to the n minus one.
That's essentially it. I guess we can multiply by 8 again minus 1, can't we? And of course, this is,
Why do we have c times a to the n minus, should that be n minus two?
no, because I multiplied this thing by 8 to the n minus 1. Right, I didn't put the C term,
Oh, I see, yeah, okay,
and this is,
yes.
and again, the fact that it's integrally closed gives that AU is in R. Everybody okay on that? So now, let me point out that if AU is a unit, then AU equals B for some B in unit of R. And so U inverse is AB inverse, which is in R. And done. Well, this is, so AU we can assume is not a unit. And so, if AU is not a unit, then so what I've done here in this case is, of course, I pulled an AUB out of it, or well, I'll pull U the n minus 1 out of this, right? That's easier to see. If B is a unit, then AU plus B is a unit. This, of course, rarely happens, but depends on the fact that this is quasi-local. And again, U is in R. Because you can divide out by this unit and you get an inequality equation for U, so it's in R. If B is not a unit, then continue. Now we've got it 1 degree less, and we just start the process over. At some point, one of the coefficients must be.
What does it mean when you say then continue?
Well, so if this is a non-unit, then just start over again with this being A prime.
Yeah, but I mean, we don't have our induction steps, so we know that one of the coefficients is a unit and you're done.
If the leading coefficient is a unit, then you're done. Right? If the leading coefficient is a unit, then you've got U in there.
We're not doing induction?
Well, that's essentially what we've done, because it's equivalent to saying, well, I could have been more careful and said, suppose
Oh,
it's
okay,
the smallest,
okay.
yeah. So we've reduced the degree down.
Sorry, I was thinking in that group and I didn't, so, okay.
Right, so is everybody okay with that, right? So A can't be a unit, AU is in here. Reduce it down to the next one. If B is a unit, you're done. If this is a non-unit, then you start it over again with a lower degree. And this process continues. But the hypothesis that at least one coefficient is a unit means at some point, this animal has to turn out to be a unit and you're done. So this is like a really groovy theorem. It's very powerful. And of course, you see in this where we use that it's interval closed a number of times. And it also depends very heavily on being quasi-local because of a unit plus a non-unit is a unit. That's important. Okay, that might be useful for homework problem. I think it was 2C. Okay. Here. Okay, any questions on that? Okay, so let's pick up where we left off, with this business about the, G domains, G ideals. And here we go. The last thing that we had last time before I had to do this is, we know that a polynomial ring, can never be a G domain, polynomial ring, over an interval domain. Proposition. I guess this is 4 through 5. Let's let R inside T be domains with T algebraic over R. And I'll clarify what that means. T algebraic over R. So you can interpret that as to be the quotient field of T is algebraic over quotient field of R, or equivalently, every element of T is a root of a polynomial equation. Well, we need to say a polynomial over R. Right. So, notice that these are equivalent because if the quotient field of T is algebraic over the quotient field of F, then take an element T and T, it's the root of some monic polynomial in F, you just include the denominators, you get this. Alright. So, I didn't give you a conclusion here. And suppose T is finitely generated over R as a ring. Over R as a ring. Then R is a G domain if and only if T is a G domain. So, actually, only one of these directions really needs finite generation as a ring. Let's let K and L be quotient fields of R and T respectively. So K is the quotient field of R and L is the quotient field of T. Suppose first that R is a G domain. And T, I'm sorry, not T, but, K is R U inverse. For some, U and, R. Then T, or I'm sorry, then TU inverse, so take that same U that you used to generate K, TU inverse is a domain that is algebraic over K. Hence, TU inverse is a field and an overlay of T. So TU inverse must be equal to L. So notice, of course, that I didn't really have to use the fact that, or I didn't need, for T to be finitely generated over, R as a ring. So on the other hand, let's suppose that T is a G domain. Now, suppose T is a G domain. And using the same notation, T equals L U inverse. For some U and T, no, actually, I'm gonna change the notation here, because that's probably the wise thing to do. And what else do we have, at our disposal to use? We have the T is finitely generated, over R's ring, so D is gonna be in T. And let's look to. So T is finitely generated as a ring over R, where the UIs, of course, are in R. That one in T as well. They're all in T, right? Wouldn't get very far with being in R. So the generating elements are all algebraic over R. Elements are algebraic over R. So, as in kind of the proof that I did before, I'm gonna write sort of abbreviated, versions of their minimal polynomials. Suppose they, are roots of polynomials, We write them with leading terms on it. So kind of whole thing, only need the leading terms, we have A, B minus N. And for all the UIs, I'm gonna call this BI. Where, of course, the A and the BIs are in R. So if we adjoin I guess I want the inverse, don't I? A inverse right. If we adjoin all these reciprocals of all these elements to R, then what do I get? So in particular, if I take the inverse of all these leading coefficients and adjoin them to R, what do I get? I get a ring containing R, but it's still an overring, right? Because these are all fractions from the quotient field of R. And so basically, I'm going to try to, and of course, the idea is, notice that these polynomial equations, if you will, over R1, these are actually monic, essentially, right? Because the leading coefficients are now all integers. And that's going to be an important piece of this here. So, notice that L is generated over R by V1 inverse U1, U2, UN. And generated over R1. But now, L1 is, not L1, L is infinite over R1. Right, because those leading terms are all units. I apologize for that. So since L is a field that's integral over R, so R1 must be a field. So K is finitely generated over R, and hence is H. Okay. Any questions on that?
Yes, so in the first direction, when we say TU inverse is a domain that is algebraic over K, and then TU inverse is a field, how do we get that?
Okay, because if you have. Everybody got this one.
Oh, well, hang on, before you do that,
Yes.
you meant to write L equals T bracket B index at the top, right?
Yes, I did. Yeah, absolutely. Thank you. Yeah, you got that just in time too. You got the faded memory of it there. Yes. Okay, so the question is, so let me make a more, here's a off the cuff dilemma. Yeah. R is a domain. That is, oh, whatever. Over field K. With R here. And will that satisfy you?
Yeah.
Right, okay, so. So let X be any non-zero element. There exists Rn minus one, R0 and R such that. And we can assume Rn and R0 are not zero, such that Rn Xn plus R1X plus R0 is equal to zero, correct?
Is Rn should be in R or in K?
Algebraical field K, yes, my bad. Thank you. X is in R, yeah. So I probably should have used different letters then, but these R's are in K. And you see, of course, it's obvious that I can choose Rn not zero, right? Because otherwise, I want to start there. Why can you choose R0 not be zero?
Otherwise you could factor out.
You can factor out the X, you can reduce the polynomial again. So here's the deal.
Subtract our knots. Factor out X.
One is equal to Rn over R naught, Xn plus R1 over R naught X, which equals X times Rn over R0, Xn minus one plus R1 over R0, and there's the inverse of X. Well, minus sign. Okay. I'm gonna leave the next one, as an exercise. It's probably a good one to work through. Proposition 436. Let's suppose R is a domain and U is an element of a larger domain. And U, an element of a domain containing R. If RU is a G domain. So I'm gonna use this lemma. Next, if RU is a G domain. Then so is R. R is the domain, and U is Alfred over R. So I'm gonna leave this one as an exercise, see if you can prove that. And so, this is where we kind of, so this V domain stuff, I think, I've always thought is kind of interesting in its own right, but we're going down a road that is going to lead to important stuff about polynomials. The Nostellan set mean, well, it's kind of like a zero set for polynomials, so we'll see what that's all about in a moment. But here is kind of the first result where connections with polynomials start to really come up. Theorem 437. The domain R is a G domain. If and only if there's a maximal ideal of its polynomial ring. Such that M intersect R is zero. Generally speaking, so here's a prime ideal of Rx such that let's call it P of Rx such that P intersect R is zero is sometimes called an upper to zero. So basically, this theorem, how can you tell if it's got a G domain? If there is an ideal, a maximal ideal of the polynomial ring that intersects down to zero. So, okay, any questions on that? Okay, so let's prove this. Um, let's let R, so let's start off in this direction. Uh, or inverse using our usual notation. So we can map Rx to K by identifying X with U inverse. So So I can map a polynomial ring into, the quotient field of R this way, just by plugging in U inverse here. Notice that since R is a Z domain, what can you say about phi?
Que no phi al máximo va bien.
Phi is onto it. Right? Therefore, the kernel of phi must be maximum. Right? Let's call this M. Now, if you look at if phi is restricted R, then right? I mean, clearly, if you restrict this down to R, this is basically just inclusion into the quotient field, so it's 1-to-1. And so the intersection of this maximal ideal, that is the kernel of this, intersect with R is 0 because there's nothing that's in R is in the kernel of this. On the other hand, suppose that M is maximal and an intersection, so let's do the other direction. Um, on the other hand, suppose M is maximal in Rx and M intersect R is 0. And the intersection is the 0 ideal. Consider projection from Rx to its quotient. For the projection map, so P of X is the cosec P of X plus M. And let Z be the image of X under this homomorphism. Note R of Z is a field. Because Rx mod M is of course a field because M is maximal, and hence a G domain. So, by the previous that we just had, R is G domain. Because it's algebraic over R. Okay, any questions on that? Okay, so let me give you a quick definition. I hope not to cloud things up too much. Let R be commuted during one and P. So this is how we've talked about this. Everything so far is in terms of domains, your G domain, and we talk about quotient fields, things being algebraic. What's the natural way to extend this to rings that are not domains? Definition. We're going to call right. An R be a runs one. A prime ideal P in R is a G ideal R mod P. Well, so now R mod P is an integral domain. That gets us back to the playground we were before. So now we can talk about G ideals, and we don't need to be living in anything other than commutative ring with identity. We say a prime ideal is a G ideal. If when I quotient out by it, I get a G domain. Let me make a first observation about this. But first, let me recall a fact. That I probably recalled before, but it ain't gonna hurt. Recall. Radical of I, which is the set of all X and R, such that X to the n is an I for some n in natural numbers, is equal to the intersection of radical of I is the intersection of all prime ideals that contain it. And so we get this really nifty corollary to this, that if you take the radical of the zero ideal, that's the intersection of all primes inside the ring. The intersection of all primes is exactly the collection of nilpotent elements. This notion of G ideals allows us to get a slightly more streamlined version of that if you ever wanted to use it. Proposition 439. Nil radical, collection of all nilpotent items, is the intersection of P is a G ideal. So, in other words, you don't have to go so far if you want the nil radical. You don't have to intersect all the prime ideals. You only have to intersect the G ideals, which sort of implies a certain abundance of them, at least enough to make that intersection the same, because on the surface of it, you might be cutting out just a whole boatload of prime ideals, but you don't cut out enough to where it messes things up, right? So, if X is nilpotent, then X is in P for all P prime. Therefore, X is in all GI. Because that's just a subset of, that was easy enough. Right, the interesting part is the other direction. And it's gonna be similar to the original proof of this, now with this flavor here. Now suppose for the other containment, suppose, that, let's suppose that U is not nilpotent. We have to convince ourselves that out there in the depths of some Stephen King novel, there is some G ideal that U is not in, right? There exists G ideal, not contained. Okay, so let's dig at this a little bit. So since 0 intersect S is empty, where S is the set of powers Q, there exists a prime ideal, call it P, such that P intersect S is empty and is maximal with respect to the property. Once again, we use this old chestnut, right? And this is a set, so we expand it to something that's maximal with respect to this property. So all we have to do now, we know that P is prime. We need to show P is a G ideal. Well, note that in R mod P, we denote the image of U by U bar. And note that every non-zero prime ideal contains U bar. Every non-zero prime ideal contains, well, of R mod P contains U bar. So R mod P is a since U is contained in every non-zero prime. So P is. And there. Okay, any questions on that? This is a good place to quit for today. I'm afraid I've got something to meet with. Anybody that wanted to meet me with office hours today from 11 to 12, please come tell me now, so we can arrange something else, because I got a call that I've got to deal with. Other than that, I will see you guys on Wednesday.